Well, let's have a look at some cubic and quartic functions today. They are lots and lots of fun. I'll help you to understand them, hopefully, a little bit better than you may have up to this point. Now, going back to quadratics, just as a little recap, even though, yes, we're only dealing with cubics and quartics in this exercise, it helps to set the scene. We've got the general form of a quadratic is y equals ax squared plus bx plus c, as you know. Now, by completing the square, as you also know, we have what's called turning point form, which is that, okay? Y equals a into x minus h all squared plus k. Now, ladies and gentlemen, this means that you can express any quadratic at all, as the sum of a perfect square, this thing, plus a constant, where the degree of x in the constant is 0. If you like, you can think of it as k x to the 0, right? Or just k. That's pretty interesting. Any quadratic at all can be expressed in that form. You know that, don't you? Well, for cubics, now, there's a trend here, and of course, as you know, the trend is your friend. So the cubic has this general form of the equation, where you've got ax cubed plus bx squared plus cx plus d. So there's one extra term there, 4 terms in there instead of 3, which you have in the quadratic trinomials. Now, by completing the cube, which I hasten to add, I don't expect you to do, and nobody expects you to do, but it is possible to complete the cube just as we complete the square up here, and the result is a most fascinating result, that you come to the conclusion that any cubic can be expressed as the sum of a perfect cube and a linear function of degree 1, whereas the quadratic was a perfect square and just a constant, which it has degree of x being 0. The cubic can be, any cubic can be expressed as a perfect cube plus a linear function of degree 1, such as x plus 1 or ax plus b or whatever you like. So that's how it goes, yeah? There it is. A into x minus h all cubed plus cx plus d. Now, here's the headline news. It is this linear function, this bit here, right, which, you know, c and d are still allowed to be 0, but they can also be non-zero as well, okay? It's completely flexible. So it's this linear function which gives rise to the variations in the shapes, all those crazy different shapes of cubics. This is very fascinating. Because of the variations in the shape of cubics, and because they come in one end of the y and go out the other end of the y, they can have no stationary points at all. They don't have to turn around at all. Or they can have one. That would be a stationary point of inflection, as we have in y equals x cubed. Or they can have 2, when you get the traditional, shape that you understand cubics to have, where they've got a maximum in one spot and a minimum in the other. But they still come in from one end of the y and go out the other end of the y. This is pretty fascinating. I'm going to show you over the screen. There's y equals x cubed, right? It comes in this end, goes out that end. This one has one stationary point, which is, actually it's a stationary point of inflection, where it's just momentarily levels off with a stationary point and then takes off again. Okay, we're momentarily being only at one point, and in this case that's where x equals 0. Okay. Now this one here, look, this one here is x cubed plus x. Now, if you think about that, guys, this is basically the perfect cube, y equals x cubed, and added to that is a linear function, y equals x, as an addition of ordinates, which we've also shown you how to do. Now, if you basically drew the graph of y equals x cubed and you draw the graph of y equals x, and if you then systematically went through and for given x values, chosen by you added up the y values of both the x cubed function and the x function, this brown graph is the shape that you would get. And how many stationary points has that one got, guys? Absolutely none. Now, if I were to go x cubed minus x, right, adding up the graph of y equals x cubed and the graph of y equals minus x, guess what shape I would get? That's what shape I would get. It's absolutely fascinating. So you get the traditional shape of a cubic with basically the maximum here and the minimum there, by adding y equals minus x to the traditional graph of y equals x cubed as an addition of ordinates exercise, that's what you get. Isn't that interesting? Yeah, so I've given you an example of no stationary points, one stationary point of inflection and two stationary points there, just by having the graph of y equals x, either, or the graph of y equals minus x, or just not having that graph at all in the case of the perfect cube y equals x cubed there. And look at the dramatic difference it makes to the shapes. This is the negative version. This is y equals minus x cubed. If I basically have the graph of minus x cubed and then add y equals minus x to that to get the graph of minus x cubed minus x, you get this shape here, right, with no stationary points in it. If you do the graph of minus x cubed plus x, then you get this same S kind of shape again, right? That's the traditional cubic shape that everybody knows so well. Isn't that fascinating? I bet you didn't know that before. Well, you might have, but anyway, it was absolutely stunningly amazing to me when I first dawned upon this fact. Now, this one here is, we've translated this graph here of y, what's this one? This is y equals x minus 2 cubed plus x minus 2. That's this one here. So that's basically the same as y equals x cubed plus x, but translated over by 2 units to the right. So where x was there before, in the original, say y equals x cubed plus x, I've replaced the x with x minus 2. That moves it over 2 units to the right. And this one here is the same thing. I've done the same thing there to x cubed minus x, except I've replaced the minus x with x minus 2, and that moves the whole graph over, compared to the one which would have had before without the x minus 2, but just had x. Y equals x cubed minus x, that would be centred there. That point there would be on the origin, but now it's on the point where x equals 2. Do you see? I hope I'm not getting too muddled in how I'm trying to explain that. I think I made it fairly clear. Now, okay, so cubics, let's have a look at the types of intercepts of cubics. This is really important too. You would have done this last year, but it's very important that we do it again now so that you can get it. Sorry about that. I hope you didn't hear that. That was the PA system. I'm at school at the moment. So, right, now we're doing types of intercepts. Now, see this one here. This is x minus 2 all cubed. And what have we got here? Now, so you see it's a cubed linear factor. When you have a cubed linear factor, it creates a stationary point of inflection. That's what it does, right? Stationary point of inflection for the x-intercept. Okay? There. You get that? Good. Now, here's another type. Okay, what have we got here? We've got a squared linear factor and just a straight linear factor. So, what does that produce? Squared linear factors produce a situation where the curve touches the x-intercept, only touches it at the point where, in this case, see, for x minus 2, it'll touch it at x equals 2, and it'll just come in, touch it, and then go away. It won't cut through it, just touches it, yeah? And therefore, that point there becomes a maximum or a minimum, a local maximum or minimum, depending on the shape of the cubic. And where you have a straight linear factor, like the x minus 4, at x equals 4, it'll cut through. That's what a straight linear factor does, just cuts through the x-axis, yeah? So that's that one there. And, yeah, straight linear factors, cuts through, and it does that there. Right? Got it? Yes. Good. Now, quartics now. The general form of a quartic is that. So ax to the 4th plus bx cubed plus cx squared plus dx plus e. Similarly, we can express any quartic at all, shocking as it may seem, as the sum of a perfect 4th and not a linear function like for the cubics or a constant number as for the quadratics, but a quadratic function of degree 2. This is the shocking revelation of the day. I reckon it's a fantastic revelation, actually. So that's how you can express any quartic, right? Now, well, what's next, Wolfman? Well, there it goes, and it is the quadratic function. It is the quadratic function which gives rise to the variations in the shapes of quartics beyond a perfect quartic, you know, classic U shape of the, if you like, of the quartic. So, yes, now, This is pretty interesting here. This is very important. Because of the variations in the shape, quartics can have... Now, do you remember I said that all even numbers like quadratics or quartics or x to the 6th or x to the 8th or whatever, they come in from the 1y direction, like plus y, and they go out the same way in the plus y. If they come in through the negative y, they'll go out through the negative y. They always go out the same way as they come in. So that means they have to turn around. They have to turn around to do that. Therefore, they have to have at least one turning point. But for the cubics and the odd ones, they don't have to. They don't have to. But these ones must have at least one turning point, stationary point, or they can have two, or they can have three. Okay, now you've got to get that. You've got to get that. The even-numbered exponent ones have to have at least one stationary point. The odd ones don't have to have any. Okay? Are you getting it? Well, come on, I'll show you. Here's x to the 4th, right? Now, look at that. There's x to the 4th minus 2x squared minus 1. Now, the quadratic component of that, if you reduce that... Well, there's the quadratic component. There, look. There's the perfect x to the 4th. And this bit here is the quadratic component, minus 2x squared plus 1, right? That minus 2x squared plus 1 is what's creating this variation with the wavy, wobbly bits here, and creating the W shape, okay? Now, there's one that's been same kind of thing but translated down, okay, downwards, yes, all right, get that? There's an interesting one there. Now, look at that one. That's a quartic with a cube repeated factor. Look, x at the origin cubed. So that creates a stationary point of inflection, just like for a cubic. But then there's an additional factor here where x, a linear factor, x minus 2 to the power 1, straight linear factor, so that cuts through the x-axis where x minus 2 equals 0 or x equals 2. Okay? Are you getting it now? See, isn't it incredible? I just think it's marvellous stuff. That's an upside down quartic, right? So that's basically, what have I got there? X minus 2 all cubed. So that's the cubic repeated factor at the point where x equals 2. So it's going to have a stationary point of inflection where x equals 2. It's got an additional one where just a straight linear factor at the origin, so that's just going to be a cut-through situation, cut through the x-axis at the origin, and this one's got a minus here, so it's a negative, upside-down quartic. Yeah, so you can work out the shape of these. Given a little bit of detective work, you know what they're going to do, okay? So quartics type of intercepts, here's the straight one, okay? That's a straight, classic U-shaped, if you like, quartic, perfect linear factor, raised to the power 4. X at the origin, x minus 0 if you like, in brackets, raised to the power 4. Okay, that's the classic shape. Yeah, the perfect fourth. Now, so what have I said there? For linear factors to the 4th power, the classic shape with the stationary max or min at the x-intercept, yeah? Now, that's there, all right? Another one. Here we've got the W shape, right? Now, this case, I call these the quadratic factors, the quadratic-y looking factors. They're repeated twice. X plus 1 squared, linear factors squared, and we've got x minus 1 squared. So that means that at at the point where x plus 1 equals 0 or x equals minus 1, you're going to have basically a situation where the curve comes and just touches the x-axis and moves away. And similarly at where x minus 1 equals 0 or x equals 1, this one will just come down and touch the x-axis where x equals 1. You see, you can work out the shape just from those two pieces of information, right? Nothing cuts through the x-axis because we don't have any just straight linear factors there. They're quadratic-y ones, squared linear factors, if you like. Now, because there's no minus sign out the front here, this is a right way up quartic, so you get the classic W shape. Yeah? So, what have I said? For squared linear factors, the curve touches the x-intercept, then changes direction so that the intercept is a max or min stationary point. There we go. Got it? How marvellous. Now, this one here, now this is a fascinating one. This is a cubed linear factor where x plus 1 equals 0 or x equals minus 1. So you get a stationary point of inflection there. This is a straight linear factor where x minus 1 equals 0 or x equals 1. So at that point it's just going to cut through the x-axis, producing the shape which we can easily predict now that we know what we're doing. So yeah, for cube linear factors, stationary point of inflection for the x-intercept there, and for the straight linear factors, the curve cuts through the x-intercept there at that. Yeah, isn't it good? Okay, I think this is the last one we're doing. Use a calculator to sketch the graph of y equals x cubed minus 2x plus 1, and then describe the transformations. Again, we're getting into transformations again. Describe the transformations to obtain the following. Y equals f of x minus 3, y equals f of x plus 3, and y equals 2 times f of x. All right, well look, here comes the graph, right? Cool, there she be, Jim. So it's difficult because look, you see it's got a really, really weird intercept. So it's difficult to do that in your head. Very difficult, but not too difficult on the calculator. Now, for the rest of this question, we're going to work out those transformations, okay? Are you happy with that? Good. So here we go. Let y equals f of x be the original function, and therefore there's our first transformation. I'm putting dashes in there to denote that this is the transformed function. Y dashed equals f of x dashed minus 3. Now, they're in equivalent form, therefore y dashed is the same as y, and x dashed minus 3 is the same as x. Now, we're stating the transformation, so therefore let's solve this for x dash y dash. There we go, it's already solved for y dashed. Now, we can see that to get from x to x dashed, you have to add 3, or go 3 units to the right. Yes? Yes, we have a translation of 3 units to the right. Now, you watch this. I've got this marvellous little graph to show you. There it is. Look, there's the original. And there, now, this is, you see, look, I haven't pulled any tricks. No tricks. It's all straight down the line stuff here. Look, x cubed minus 2x squared. Is that plus 1? Yes, I'm a bit blind here. Yeah, plus 1. Now, this function here I just said is the other function, but with an x minus 3. Okay, that's f21 of x. This is f22 of x, which is just f21 of x minus 3, which is what we were doing up here. And look how it moved it over. It moved it over 3 units to the right. Yes, it's pretty good, isn't it? It's excellent. That's what I think. Now, yes, yes, yes. Okay, what's this one now? Yes, this is the second transformation. Y equals f of x was the original function. Y dashed equals f of x dash plus 3 is the transformed function, and do the same old thing we did before. Equivalent form, therefore y dashed equals y, therefore x dashed plus 3 equals x, and therefore x dashed is x minus 3, which means we're moving over. Come on, what are we doing? To get from x to x dashed, what do you got to do to x? You've got to take 3 off it, or move it 3 units to the left. And there it is, there's the graph. Look, see? This one is f21 of x, this one's f22 of x, which is, except I've got an x plus 3 there. It's f21 of x plus 3, which moves it over to the left by 3. Yes? It's mighty fine, that's what it is. Now, there you go, there you go. Okay, now the last one, and then I think we might be finished. Okay, that was, what was that one again? Y equals f of x was the original function, yes. Y was 2f of x, right? So we're putting y dashed is 2 times f of x dashed. Now that 2 has got to be attached to something, and the best, easiest thing to do is to attach it to the y. So y dashed over 2 equals f of x dashed. Now they're in equivalent form. So y dashed is the same as y over 2, equating the two left-hand sides, if you like. And of course, yes, and therefore an x dashed is just the same as x, yes? So therefore, what have we got to do to y to turn it into y dashed, guys? We add a dilation of a factor of 2, making it twice as high, which is from the x-axis, yes? Okay, here you go. You ready? Roll the drums. Take a deep breath. It's very, very amazing. Look! Look, look, look. This is the brown graph, the original graph. Now, it was dilation of a factor of 2 from the x-axis. So you'll see everything's stretched. Look, that was 0.1 on the brown graph. It's 0.2 on the blue graph. But where it goes through the x-axis, of course, that's not going to stretch anything because 2 times 0 is 0, isn't it, for the y value? Again, same thing here, where it cuts through the x-axis, the y value is 0, 2 times 0 is 0. And same thing here, but you'll notice here, look, this blue bit is exactly double what the brown bit is for that particular value of x, because it's stretched, dilated by a factor of 2 from the x-axis. And you can see the trend is everywhere, the same thing, through when you're comparing the blue graph with the brown graph. I just thought that was marvellous when I did that. So I hope you enjoyed that. That's that, yes, it's, what is it? Oh, 2 times, yeah. So f22 of x in this case is 2 times f21 of x, which is what we were told to do up here. Yes, I think that's the end. I think the star's coming. Yes, hello Mr. Star. And you're a star. And of course you know that you'll go far if you do plenty of practice. You might not get too far if you don't do any practice. So please go off and do some practice and get really good at these and have a marvellous time while you're doing it. And I will see you next time. Bye-bye.